Assalamu alaikum everyone. My name is Aliha Jannat and today I'm going to present the topic of Zwitterionic hydrogels. In this topic, we will cover the basic concepts of hydrogels, then explain what makes Zwitterionic hydrogels special, followed by their chemistry, synthesis methods, properties, mechanical reinforcement strategies, applications, challenges, and future directions. So first of all, let's start with what are hydrogels. Hydrogels are basically three-dimensional cross-linked polymer networks that can absorb and retain very large amount of water. In many hydrogels, the water content is more than 80% by weight. Because of this very high water content, hydrogels closely resemble soft biological tissues like cartilage in terms of flexibility, softness, and mechanical behavior. That is why hydrogels are widely used in biomedical fields such as wound dressing, tissue engineering, and drug delivery. Now, let's understand what are Zwitterionic hydrogels. In these hydrogels, each repeating unit of polymer chain contains both a positive and a negative charge at the same time. The positive charge is usually a quaternary amino group, while the negative charge can be sulfonate group, a carboxylate group, or a phosphate group. These two opposite charges are present within the same monomer unit and are separated by a short spacer of 1 to 3 carbon atoms. Because these positive and negative charges balance each other, so the polymer has no overall net charge, but still it is highly polar. The internal charge balance is extremely important. Even though the polymer is electrically neutral, overall the presence of strong local charges creates a very strong interaction with the water molecules. Because of which Zwitterionic hydrogels show exceptionally strong hydration, making them much stronger than conventional hydrogels, such as polyethylene glycol based systems. If we talk about the design of hydrogels, so it is inspired by the nature. Many biological molecules are zwitterionic in nature. For example, if we talk about phosphatidylcholine, which is a major component of cell membrane, and betaine, which is a natural osmoprotectant molecule found in the cell. Basically, it is a molecule that prevents the dehydration of our cells. Because Zwitterionic hydrogels mimic these natural structures, they show excellent biocompatibility and stability in biological environments. One of the most important properties of Zwitterionic hydrogels is their strong hydration behavior. Each Zwitterionic unit can bind approximately 7 to 8 water molecules through strong ion dipole interactions, while on the other hand, PEG based hydrogels typically bind only 1 to 2 water molecules per unit. This difference explains why Zwitterionic hydrogels show much better resistance to protein adsorption and biofouling. Now, let's move toward thermodynamic explanation of antifouling behavior. But before that, we must understand what is antifouling behavior. So we can say that it is the ability of a surface to resist the adsorption of unwanted molecules. This behavior can be explained by using thermodynamics Gibbs free energy equation, which is delta G is equals to delta H minus T delta S. Here, delta G represents Gibbs free energy, delta H represents enthalpy change, T represents temperature, and delta S represents change in entropy. In Zwitterionic hydrogels, the hydration layer is very tightly bound, and when a protein or bacteria wants to adsorb on its surface, they first have to remove this hydration layer. But removing this layer requires a large amount of input energy. It means delta H become positive, due to which the value of Gibbs free energy also become positive. This positive value indicates that the reaction cannot proceed naturally or spontaneously. So protein adsorption becomes thermodynamically unfavorable. This is why proteins, cells, and bacteria do not stick to zwitterionic hydrogel surfaces easily. Recent studies in 2025 have further improved these materials by designing mechanically strong networks, fatigue resistant hydrogels, and skin inspired structures with enhanced water retention. Another unique feature of zwitterionic hydrogels is their anti-polyelectrolyte effect. Normally, polyelectrolyte hydrogels collapse in salty environment, as you can see in the diagram, due to the charge screening. However, zwitterionic hydrogels behave in an exact opposite way. When the salt's concentration increases, the added ions screen the internal electrostatic attractions in zwitterionic hydrogels, due to which polymer chains relax and become more flexible. That's why the hydrogel swell instead of collapsing. This unusual behavior is called anti-polyelectrolyte effect and makes zwitterionic hydrogels very stable in physiological fluids like seawater and desalination environments. Now, if we look at this figure shows a Zwitterionic hydrogel network. You can see polymer chain containing both positive and negative charges. Around these charge groups, there are multiple layers of tightly bound water molecules, forming what we call a hydration shell. This figure also contrasts Zwitterionic hydrogels with traditional polyelectrolyte gels. In polyelectrolyte hydrogels, when salt is added, the polymer chains collapse due to charge screening because the electrostatic forces of attraction reduces. However, in deuterionic hydrogels, the opposite happens. When the salt is added, internal electrostatic attraction are screened, allowing the polymer chains to expand. This phenomena is known as anti-polyelectrolyte effect, and it is defining feature of deuterionic hydrogels. Because of this antifouling behavior, low immune response when implanted in body, stability in high salt environment, compatibility with biomedical and environmental applications, Zwitterionic hydrogel solves several long-standing problems at the same time. Now let's move toward the structure and fundamental chemistry of Zwitterionic hydrogels. The behavior of Zwitterionic hydrogels is mainly controlled by how positive and negative charges are arranged inside the polymer chain. In most Zwitterionic hydrogels, the polymer is built from betaine-type monomers. A betaine monomer usually contains a permanently charged cation, usually a quaternary ammonium group, while the negative charge groups can be sulfonate, carboxylate, or phosphate. Both charges are present within the same repeating unit, which makes the polymer electrically neutral but highly polar. The distance between the positive and the negative charge is also very important. Usually, the charges are separated by 1 to 3 methylene groups. If the charges are too close, strong electrostatic attraction can cause the chain contraction, and if the charges are too far apart, hydration density decreases. So, an optimal spacing produces strong dipoles and maximum hydration, which is essential for anti-fouling behavior. Now, we will discuss the three major types of zwitterionic monomers. The first one is polysulfobutane methacrylate. In this monomer, the cationic group is trimethyl ammonium group and the anion group is sulfonate group. These groups are separated by a short propyl spacer. Because the charges are close, strong dipole-dipole interactions occur between polymer chains. In pure water, these attractions can cause temporary chain contraction, which lead to upper critical solution temperature behavior where the molecule collapses at low temperature. While the next monomer is polycarboxybutane methacrylate. In this polymer, the anionic group is carboxylate instead of sulfonate group found in sulfobutanes. This structural difference introduced pH sensitivity into the material. At physiological pH, which is approximately 7.4, the polymer remains electrically neutral, maintaining strong hydration and show excellent antifouling performance. However, under acidic condition, the carboxylate group can become protonated. This protonation slightly alters the internal charge balance of the polymer, which in turn affects the swelling behavior. Because of this controlled pH responsiveness, carboxybutane methacrylate is particularly valuable for medical applications, where materials are often exposed to varying pH environment. The third important deuterionic polymer is MPC. This polymer contains a phosphoryl group which is chemically very similar to the head group found in the cell membranes. Due to this close biomimicry, MPC exhibit outstanding biocompatibility and extreme low protein adsorption. As a result, it has been widely used in contact lenses, vascular stents, and other blood contacting medical devices, which minimize biofouling and immune response is critical. If we talk about the molecular structure and hydration chemistry, So, the hydration behavior of zwitterionic hydrogels is exceptionally strong because zwitterionic monomers possess very large dipole moments, often exceeding 20 dBi. This strong dipole attracts water molecules primarily through ionic solvations rather than simple hydrogen bonding. As a result, water molecules arrange themselves into dense and tightly bound hydration shells around the charge groups. These hydration layers are highly stable and remain intact even in the salt-rich environment, which explains why zwitterionic hydrogels maintain their properties under physiological and marine conditions. It is important to clearly distinguish between the zwitterionic polymers from polyampholytes, as they are often confused. Polyampholites are formed from separate ionic and cationic monomers, and their overall charge balance depends on precise monomer composition. If this balance changes, their anti-fouling performance can decrease. In contrast, zwitterionic polymers maintain internal charge neutrality within every repeating unit of the polymer chain. Because this balance is built directly into the molecular structure, zwitterionic polymers exhibit more stable and reliable antifouling behavior across a wide range of conditions. Electrostatic interactions with zwitterionic polymers also play a key role in swelling behavior. In pure water, oppositely charged groups along the same polymer chain can attract each other, creating temporary physical crosslinks that slightly contract the chains. However, when the salt is added, external ions screen these internal electrostatic attractions. This screening allows the polymer chains to expand, leading to an increased swelling. This counterintuitive swelling behavior is known as anti-polyelectrolyte effect, and it explains why hydrogels perform so well in physiological fluids and marine environment where high salt concentrations are present. If we look at this table compares different types of zwitterionic monomers and summarizes the monomer type, representative examples, the cationic and anionic groups, the key functional features, and the number of water molecules bound per repeating unit. If we talk about sulfobetanes, such as SPMA, typically bind 7 to 8 water molecules per unit and are characterized by strong dipole-dipole interactions, while carboxybetanes can bind slightly fewer water molecules, around 6 to 7, but offer the important advantage of pH responsive charge neutrality. Phosphobetanes show the highest hydration by approximately 8 to 9 water molecules, which is attributed to strong hydration ability and of the phosphate group and its similarity to natural cell membrane components. In contrast, polyampholites bind fewer water molecules, typically around 5 to 6, and their hydration strongly depends on maintaining charge balance. Overall, the table clearly demonstrates why true zwitterionic polymers outperform other charged hydrogels in terms of hydration strength and antifouling performance. Now let's have a look at this figure. This figure here presents the chemical structure of sulfobetane methacrylate, carboxybetane methacrylate, and MPC side by side. In all these structures, the presence of quaternary ammonium group is clearly visible, which provides the positive charges. The key difference lies in the anionic groups, which are sulfonate in SPMA, carboxylate in CBMA, and phosphate in MPC. This figure highlights how small variations in chemical structures can lead to major differences in hydration behavior, pH sensitivity, and biological performance. By comparing these structures visually, it becomes easier to understand why zwitterionic polymers are selected for specific biomedical and engineering applications. Synthesis and fabrication methods. After understanding the molecular structure and chemistry of zwitterionic hydrogels, the next important topic is how these materials are actually synthesized and fabricated. The synthesis methods directly controls the network structures, crossing density, mechanical strength, swelling behavior, and long-term stability of hydrogels. In the recent years, researchers have focused on developing synthesis routes that are simple, scalable, and compatible with the sensitive zwitterionic functional groups, while also allowing precise control over the final material properties. So let's discuss the first synthesis method, which is free radical polymerization. Free radical polymerization is one of the most widely used method because this is simple, versatile, and suitable for large-scale production. In free radical polymerization, polymerization occurs through three main steps: initiation, propagation, and termination, which together create a three-dimensional cross-linked polymer structure. The process begins with initiation, where a thermal initiator such as ammonium persulfate decomposes upon heating. This decomposition generates sulfate radical species, which are highly reactive. These sulfate radicals react with water to form hydroxyl radicals, and these hydroxyl radicals then attack the vinyl double bond present in the zwitterionic monomers, such as sulfobutane methacrylate. As soon as the radical adds to the monomer, a new reactive radical center is created on the polymer chain. The next step is propagation. During the propagation step, this activated radical continues to react with additional zwitterionic monomers. Each successive monomer addition extends the polymer chain while maintaining the zwitterionic side groups intact because each repeating unit contains both positive and negative charges. The growing chains remain electrically neutral but highly polar throughout the process. The final stage is cross-linking and termination. Here, bifunctional cross-linkers such as methylene bisacrylamide react with two different polymer chains, forming covalent bridges between them. This converts the linear polymer chains into a permanent three-dimensional hydrogel network. Termination occurs when two radical chains combine or when a radical reacts with an inhibitor. The amount of cross-linkers used play an important role. If low amount of cross-linkers is used, they produce soft and highly swollen hydrogels, while higher concentration produce stiff but more brittle networks. This figure here illustrates the free radical polymerization process of sulfobutane methacrylate hydrogels. This figure shows how the zwitterionic monomers in the presence of an initiator and a crosslinker form a covalently cross-linked network. You can see the polymer chains growing and being interconnected through cross-linking points, resulting in a stable hydrogel structure that retains zwitterionic side groups responsible for hydration and anti-fouling. The next method of synthesis is photopolymerization method. In this method, polymerization is initiated using ultraviolet light rather than heat. Photoinitiators such as Irgacure 2959 absorb UV light and split into radical species. These radicals then initiate polymerization in the same way as thermal radicals by attacking the vinyl group of the zwitterionic monomers. The advantage of photopolymerization is that it occurs at room temperature and allows very precise control over and when and where gelation happens. This makes it especially useful for fabricating thin coating patterned hydrogels and biomedical devices where spatial control is important. In addition to UV-based systems, redox-initiated polymerization is also widely used. In the redox system, ammonium persulfate reacts with EMED, which is tetramethyl diamine, to generate radicals through an electron transfer mechanism. This approach allows rapid gelation without the need for heating or light, making it suitable for in situ hydrogel formation in biological environments. The next method of synthesis is double network hydrogel synthesis. To overcome the mechanical weakness of conventional zwitterionic hydrogels, double network hydrogel synthesis have been developed. In this approach, two interpenetrating polymer networks are formed sequentially within the same material. The first network is highly cross-linked and rigid, while the second network is loosely cross-linked and flexible. The first network is designed to act as a sacrificial network. Under the mechanical stress, this rigid network fractures and dissipates energy. The second network, which is more elastic and ductile, maintains the overall structural integrity of the hydrogels. When the Zwitterionic polymers are incorporated into one or both of these networks, the hydrogel achieves a combination of high mechanical strength and excellent anti-fouling behavior. In practice, The first network is synthesized by using a high concentration of crosslinker, while the second network is formed using a much lower crosslinker concentration. This design is dramatically increases the tensile strength, elongation, and fracture energy, making the double network Zwitterionic hydrogel suitable for load-bearing and mechanically demanding applications. Another important fabrication strategy involves dynamic and reversible cross-linking. In these hydrogels, the network is held together not only by the permanent covalent bonds but also by reversible interactions, such as metal ligand coordination or supramolecular bonding. For example, a multivalent metal ion like bismuth ion can coordinate with sulfonate groups present in sulfobutane polymer. These metal ligand bonds can break under mechanical strength and then reform once the stress is removed. This reversible behavior allows the hydrogels to self-heal after the damage and recover most of its mechanical strength over time. For example, dynamic cross-linking provide an effective way to improve toughness and durability without sacrificing hydration and anti-fouling properties because Zwitterionic groups remains available to bind water even when participating in reversible interactions. The next method of synthesis is nanocomposite hydrogel fabrication. Nanocomposite Zwitterionic hydrogels are fabricated by polymerizing Zwitterionic monomers in the presence of nanoscale fillers such as clay nanoparticles, graphene oxide, or cellulose nanocrystals. These nanofillers interact with the polymer chains through electrostatic interactions and hydrogen bonding, acting as physical cross-linking points. The presence of nanofillers allows stress to be transferred more efficiently throughout the network. Polymer chains can slide along the surfaces of the nanofiller, which dissipate energy and increase mechanical strength without significantly reducing water content. As a result, the nanocomposite Zwitterionic hydrogels often show several-fold improvements in toughness and durability compared to the neat hydrogels. Injectable Zwitterionic hydrogels. Injectable Zwitterionic hydrogels are designed to form directly at the site of application. In these systems, liquid precursors are injected and then cross-linked to rapid and mild chemical reactions. One commonly used approach is thiol-ene-click chemistry, where thiol groups react with alkene groups to form stable covalent bonds. This reaction proceeds quickly without the need for toxic catalyst or harsh conditions, making it highly suitable for biomedical usage. Injectable Zwitterionic hydrogels enable minimally invasive treatments and are widely explored for wound healing, tissue engineering, and localized drug delivery like applications. Now let's see which kind of physiochemical properties are possessed by Zwitterionic hydrogels. The most important properties include superhydrophobicity, antifouling behavior, ion conductivity, salt and pH responsiveness, and mechanical performance. These properties arise directly from the unique molecular structure and are responsible for their outstanding performance in biological and engineering environment. So first of all, we are going to explore its superhydrophobicity and surface hydration. The most fundamental property of Zwitterionic hydrogel is that they are super hydrophilic. This means that they have an exceptional strong affinity for water. The positive and negative charges present in each Zwitterionic unit attract water molecules through ion dipole interactions. As a result, water molecules form tightly bound and highly ordered hydration layer around the polymer chains. These hydration layers are much more stable than hydrogen bonding water layers found in neutral gels, such as PEG, polyethylene glycol based hydrogels. Because the water molecules are strongly bound, they are not easily displaced. This leads to the extremely low levels of protein adsorption, often below zero point 0.3 nanograms per square centimeter, which is considered near zero fouling. The next property is anti-fouling and low immunogenicity. Because of their strong hydration layers, Zwitterionic hydrogels exhibit exceptional antifouling properties and very low immunogenicity. Because the biomolecule do not get adsorbed easily, so platelets are not activated and hemolysis is minimal. Experimental studies show that the bacterial adhesion on the Zwitterionic hydrogel surfaces is often less than 1% as compared to the conventional materials. This low level of biological interaction significantly reduces inflammation and foreign body reactions when these materials are implanted in the body. As a result, Zwitterionic hydrogels are highly suitable for blood contracting devices, implants, and long term biomedical applications. Another important physiochemical property of Zwitterionic hydrogels is ionic conductivity. Although the polymer chains are electrically neutral overall, the charge groups can partially dissociate under an applied electric field. This allows the ions to migrate through the hydrated network. Because the hydrogels contain a large amount of water and mobile ions, ionic conductivity can be quite high. Some Zwitterionic hydrogels can reach conductivities of several tens of millisiemens per centimeter. This property is especially valuable for applications in bioelectronics, wearables, sensors, and energy storage devices. Salt and pH responsiveness. Zwitterionic hydrogels display a unique response to salt known as polyelectrolyte effect. In pure water, electrostatic attractions between oppositely charged groups along the polymer chain act as temporary physical crosslinks, slightly restricting swelling. When the salt is added, external ions screen these internal attractions. This screening effect causes the polymer chains to expand, leading to increased swelling rather than collapsing. The swelling ratios increase with the salt concentration, which is the opposite behavior of conventional polyelectrolyte hydrogels. These properties allow Zwitterionic hydrogels to remain swollen and functional in physiological fluids and seawater. If we talk about the pH responsiveness in Zwitterionic hydrogels containing carboxybutane units, pH responsiveness is also observed. At physiological pH, the carboxylate groups remains deprotonated and the polymer remains electrically neutral. Under acidic conditions, partial protonation occurs when which alters the internal charge balance and charge swelling behavior. These pH sensitivity allows Zwitterionic hydrogels to respond to the changes in their environment, making them useful for controlled drug release and smart biomedical systems. Here, if we look at the figure, we'll get to know that it illustrates the mechanism of anti-polyelectrolyte effect as we have already discussed earlier. This figure shows polymer chains in pure water forming a compact structure due to the internal electrostatic attractions. As you can see here, the chains are very close to each other because the positive and negative charges are attracting each other. When the salt is added, these attractions are screened by the external ions, allowing the chains to expand and the hydrogen gel to swell. This visual representation helps to explain why Zwitterionic hydrogels behave differently from conventional charged hydrogels in saline environment. Mechanical properties. Despite the excellent hydration, Zwitterionic hydrogels are often mechanically weak when used alone. Neat Zwitterionic hydrogels typically exhibit fracture stress below 2 megapascals. However, the presence of dynamic ionic interactions allow for self-healing behavior. When the hydrogel is damaged, reversible interactions such as metal-ligand coordination or ionic association breaks and then reforms over time. This enables recovery of the mechanical strength, sometimes reaching more than 90% of the original strength within a day. In addition, Zwitterionic hydrogels show excellent lubrication properties with extremely low coefficients of friction, which is useful for joint lubrication and soft tissue interfaces. Zwitterionic hydrogels also show remarkable tolerance to extreme conditions in the presence of salt. They can resist freezing at very low temperatures, sometimes as low as minus 70 degrees Celsius. This anti-freezing behavior is due to the strong interaction between water, ions, and Zwitterionic groups, which prevents ice crystallization. The table here compares the neat, double network reinforced and nanocomposite Zwitterionic hydrogels in terms of swelling, mechanical strength, conductivity, and anti-fouling performance, along with representative values. Neat hydrogels show high swelling above 80%, but very low tensile strength of 2 megapascal. After Double network reinforcement swelling remains high at about 150 to 300% even in the saline environment, while the tensile strength increases dramatically to around 8 megapascal due to sacrificial bond mechanisms. Nanocomposite hydrogels display a stable swelling in and moderate strength. For example, about 0.6 megapascal achieved through nanoparticle reinforcement. Conductivity improves from 1.5 Siemens per meter in each gels to a 32 Siemens per meter in double network systems, with reported values of 30 Siemens per meter even at minus 40 degrees Celsius due to the efficient ion migration. Importantly, protein adsorption remains extremely low in all the cases, typically below 1.5 nanogram per cubic centimeter and approaching zero, because the hydration barrier of Zwitterionic groups is preserved. Overall, the table highlights how reinforcement strategies enhance mechanical and transport properties while maintaining excellent antifouling performance. Mechanical reinforcement strategies. Up to this point, I have explained that Zwitterionic hydrogels possess excellent hydration, antifouling behavior, and biocompatibility. But one major limitation of these hydrogels is their poor mechanical strength, because they contain a very high amount of water and relatively weak interchain interactions. Zwitterionic hydrogels are often soft, brittle, and prone to fracture under stress. Therefore, mechanical reinforcement strategies are essential to make these materials suitable for practical and load-bearing applications. Double network hydrogels. One of the most successful reinforcement strategies is the design of double network hydrogels. In this approach, two interpenetrating polymer networks are formed within the same hydrogel. The first network is highly cross-linked and rigid, while the second network is loosely cross-linked and flexible. If you scroll down to the diagram, here you can see the rigid network has been shown by the red lines, while the ductile network or soft network is shown by the blue lines. When the mechanical stress is applied, the rigid first network breaks sacrificially. This fracture dissipates a large amount of energy, preventing catastrophic failure. At the same time, the soft second network stretches and maintains the overall integrity of the hydrogels. When Zwitterionic polymers are used as a second network, the hydrogel retains its antifouling and hydration properties while achieving significantly improved mechanical strength. Double network Zwitterionic hydrogels can achieve tensile strength above 1 megapascal and fracture energies exceeding 1000 joules per square meter. These values are comparable to the natural tissues such as cartilage, making them suitable for biomedical implants and soft tissue substitutes. Nanocomposite hydrogels. Another effective strategy for mechanical reinforcement is the fabrication of nanocomposite hydrogels. In these systems, nanoscale fillers such as cellulose nanocrystals, clay nanoparticles, or graphene oxide sheets are incorporated into the Zwitterionic polymer network. These nanofillers act as multifunctional physical cross-linking points. They interact with the polymer chains through electrostatic interactions and hydrogen bonding. Under mechanical stress, polymer chains can slide along the surfaces of the nanofillers, allowing stress to be distributed more evenly throughout the network. This sliding mechanism dissipates energy and significantly increases toughness and durability. Importantly, because the nanofillers are present at low concentration and are well dispersed, they do not significantly reduce water content or disrupt the hydration layers responsible for antifouling behavior. Topological or slide ring hydrogels. A more advanced reinforcement strategy involves topological hydrogels, also known as slide ring hydrogels. These materials are based on polyrotaxane structures, where the ring-shaped molecules such as cyclodextrins are threaded onto the polymer chains and then locked in place by bulky end groups. In these hydrogels, the crosslinks are not fixed at specific points but can slide along the polymer backbone. The sliding motion allows the stress to be distributed evenly throughout the network, preventing localized stress, concentration, and crack initiation. As a result, topological hydrogels exhibit extremely high stretchability and toughness. When the Zwitterionic monomers are incorporated into these systems, the hydrogel combines exceptional mechanical resilience with excellent anti-fouling and hydration properties, making it a promising design for the next generation soft materials. The figure here shows three ways to mechanically strengthen Zwitterionic hydrogels. In the double network system, as you can see, there is a rigid first network breaks sacrificial bonds to absorb energy, while a soft network maintains the gel integrity. In nanocomposite hydrogels, dispersed nanoparticles reinforce the polymer chains and helps to distribute the applied stress, increasing strength and toughness. While in the slide ring or topological hydrogels, movable ring crosslinks slide along the polymer chains, preventing stress concentration and allowing high stretchability. Overall, the figure explains how these designs improve mechanical robustness without losing hydration and anti-fouling properties. Applications of Zwitterionic hydrogels. Because of their unique properties, Zwitterionic hydrogels are now widely explored in biomedical, environmental, and engineering fields. So, first of all, let's discuss biomedical applications. Among the biomedical applications, the most important and widely studied application of Zwitterionic hydrogels is anti-fouling interfaces for implants and devices. Zwitterionic hydrogels resist non-specific protein adsorption and cell adhesion. Thanks to their dense hydration layers, the ion dipole interactions between zwitterionic groups such as sulfobutane, carboxybutane, and phosphorylcholine and water creates a tightly bound shell. Protein must expend significant energy to displace this hydration layer, which suppresses adsorption and fouling. Unlike traditional polyelectrolyte, zwitterionic hydrogels maintain the protection even in saline or protein-rich conditions, showing ultra-fouling less than 5 nanograms per cubic centimeter. The materials have been applied to catheters, stents, contact lenses, and biosensors, reducing thrombosis, bacterial adhesion, and inflammatory responses. Recent studies have also showed that the coating which contains deuterionic monomers are both durable and self-healing, preventing antifouling performance even after the mechanical stress and long-term immersion. If we talk about surface engineering, high-density polymers brushes are grafted via ATRP and draft to maximize hydration, while covalent anchoring through silanes and catechol-based primers ensure long-term stability. Injectable hydrogels, wound dressing, and tissue engineering. Injectable hydrogels start as liquids and then turn into the gels directly at the site where they are applied, such as wound or damaged tissues. This gel formation happens through safe chemical reactions like light activated cross-linking, redox reaction, or simple click reactions. These reactions lock the polymer chains together while keeping the zwitterionic groups intact, so the gel stays highly hydrated, resists proteins and bacterial attachment, and remains biocompatible. To form the gel network, common crosslinkers are used. In some cases, metal ions are added to create reversible ionic links, which allow the gels to self-heal and become tougher without losing its anti-fouling properties. Because these hydrogels are soft, injectable, and friendly to cells, they are widely used in wound healing, tissue engineering scaffolds, and for delivering cells. Growth factors and bioactive peptides can also be attached to the hydrogel, so it's not only fills the damaged area but actively supports tissue repair and regeneration. The next application is drug delivery and controlled release. In drug delivery, zwitterionic hydrogels can carry medicines in two main ways. Either the drug is physically trapped inside the gel network or it is chemically attached to the polymer using bonds that can later break. However, how fast the drug comes out depends upon how tight the hydrogel network is, meaning the pore size and how densely the chains are cross-linked. Drug release is also influenced by the interactions inside the gel. Some drugs stick to the polymers through ionic interactions while others sit inside small hydrophobic pockets. Zwitterionic hydrogels can respond to changes in salt concentrations. When salt screens the internal charges, the gel swells, the pore opens, and the drug diffuses out faster. This makes controlled or stimulus triggered release possible. In some designs, drugs are attached through special linkages like esters or hydrazone bonds, which break under certain pH conditions or through hydrolysis, releasing the drug at the right place. Adding a small amount of hydrophobic monomers, tiny hydrophobic regions inside the gel that holds the drugs longer, allowing slow and sustained release. Here is a diagram which shows the possible biomedical applications of Zwitterionic hydrogels. As you can see, it is used in anti-fouling implants, tissue engineering, injectable hydrogels in wound dressing, and drug delivery systems. The next application is marine and anti-fouling coatings. Zwitterionic hydrogels are also explored as marine anti-fouling coatings. In marine environments, surfaces are rapidly colonized by algae, barnacles, and bacteria. Traditional antifouling coatings often rely on toxic chemicals. These hydrogels offer a non-toxic alternative. Their hydration layers prevent the initial attachment of marine organisms, reducing biofouling without harming the environment. Next are environmental applications. In environmental applications, Zwitterionic materials are mainly used to solve fouling and water scarcity problem. When Zwitterionic coatings are applied to desalination or water treatment membranes, they prevent bacteria and organic matter from sticking to the surface. This keeps the water flow stable and efficient even in the salty or brackish water. In atmospheric water harvesting, Zwitterionic hydrogels are combined with salt or special porous materials like metal organic frameworks to absorb water directly from the dry air. The hydrogel hold the salts in place and absorb moisture, and collected water can be released easily during mild heat or sunlight, making it useful for off-grid water collection. If we talk about sensors, wearables, and bioelectronics, Zwitterionic hydrogels act as soft ion conducting materials. They stay wet and resist fouling. This makes them ideal for skin mounted sensors, bioelectrodes, and even underwater electronics. In biosensors, Zwitterionic coatings reduce unwanted protein sticking, which lowers background noise and allow the sensors to detect target molecules more clearly and accurately. Energy and electrochemical devices. In electronic devices, hydrogels function as solid or semi-solid electrolytes. They efficiently conduct ions, enabling smooth charge transport while stabilizing the electrode and electrolyte interface. Their soft hydrated structure helps to suppress metal dendrite formation, which is a major cause of short circuit in batteries. Incorporating salts into hydrogels increase ionic conductivity while the addition of nanoparticles enhance the mechanical strength and improves the contact with electrodes. Together, these features improve the safety, stability, and operational lifetime of the electrochemical devices. Soft robotics and actuators. Zwitterionic hydrogels can act as soft robotic actuators because of their dynamic crosslinks and ionic conductivity. The dynamic crosslinks let them self-heal while the ionic conductivity allows them to carry electrical signals. By applying electrodes or creating a cross-linking gradient, the hydrogels can bend, stretch, and move in a controlled and programmable way, making them ideal for soft robotics and wearable devices. Comparison with other hydrogels. Hydrogels can generally be categorized into neutral hydrogels, anionic or cationic hydrogels, polyelectrolyte hydrogels, and zwitterionic hydrogels. Each of these classes has distinct interactions with water, protein, and biological environments, which directly affect their suitability for various applications. So, first of all, we will compare neutral hydrogels versus zwitterionic hydrogels. First, consider neutral hydrogels such as polyethylene glycol, polyvinyl alcohol, or polyacrylamide. These materials do not contain ionizable groups, so their interaction with water is dominated by hydrogen bonding. Hydrogen bonding allows these hydrogels to swallow and absorb water, but the hydration layer is relatively weak and can be easily disrupted in complex biological environment. Polyethylene Glycol-based hydrogels are widely used because of their good biocompatibility, but their anti-fouling performance is limited. Over time, polyethylene glycol chains can be oxidized in vivo, and protein may eventually adsorb to the surface. In contrast, Zwitterionic hydrogels form hydration shells that are ionically bound rather than just hydrogen bonding. This makes the water layer denser, more stable, and resistant to displacement, even under high salt or extreme pH environment. As a result, Zwitterionic hydrogels demonstrate near zero fouling, whereas PEG and other neutral hydrogels are only low fouling. If we look at the figure here, this figure compares the hydration in PEG-based and Zwitterionic polymers. PEG relies on weak and dynamic hydrogen bonding, forming a loose hydration layer that can degrade under salt, temperature changes, or long-term use. On the other hand, Zwitterionic polymers bind through strong electrostatic and ionic interactions, creating a dense and stable hydration shell. This explains their superior antifouling performance and long-term stability as compared to the PEG. Anionic and cationic hydrogels versus Zwitterionic hydrogels. Anionic hydrogels such as polyacrylic acid and alginate and cationic hydrogels such as chitosan or polyethylene imine contains a net charge along their polymer chains. This net charge causes strong electrostatic repulsion between like charges, which leads to high swelling in deionized water. However, in saline environment, counterions screen these charges, causing the hydrogen network to collapse because of the reduction in electrostatic repulsion. This reduces their swelling capacity and mechanical stability. Moreover, the net charge also promotes non-specific interactions with the proteins, cells, and biomolecules, which can lead to biofouling, cytotoxicity, and immune reaction. In contrast, Zwitterionic hydrogels maintain overall neutrality. While they contain both positive and negative charges, they are internally balanced, preventing a long-range electrostatic attraction with biomolecules. Combined with strong local dipole water interactions, this ensures excellent hydration, swelling stability, and antifouling behavior even in saline or physiological conditions. Polyelectrolyte hydrogels versus Zwitterionic hydrogels. If we compare polyelectrolyte hydrogels with Zwitterionic hydrogels, we come to know that polyelectrolyte hydrogels contain polymer chains with multiple ionizable groups that require mobile counterions to maintain the charge balance. Their swelling behavior is largely controlled by Donan osmotic pressure, which allows high water uptake but makes them sensitive to changes in ionic strength. This sensitivity can lead to unpredictable volume changes and mechanical instability in physiology or marine environments. Deuterionic hydrogels, on the other hand, do not rely on the counterions because each monomer contains internally balanced charges. This design minimizes osmotic pressure effects and result in improved dimensional stability, predicts swelling, and even more reliable mechanical performance. These characteristics make Zwitterionic hydrogels superior in applications where the environmental ionic conditions fluctuate, such as in seawater, blood, or brackish water. Mechanical and biological performance comparison. One limitation of Zwitterionic hydrogel has historically been relatively low mechanical strength due to high water content and reduced interchain associations. Conventional ionic hydrogels can be mechanically strengthened by adding ionic crosslinks, but this often compromises antifouling behavior because the surface becomes more attractive to proteins and cells. Recent reinforcement strategies such as double network formation, nanocomposite incorporation, and dynamic cross-linking have largely addressed this issue. Deuterionic hydrogels can now achieve tensile strength exceeding 1 megapascal while retaining their ultra-low fouling properties. Biologically, Zwitterionic hydrogels consistently outperform other hydrogel classes. They resist protein adsorption, minimize unwanted cell adhesion, and show excellent hemocompatibility and immune inertness, making them ideal for long-term implantable devices and advanced biomedical interfaces. If we look at the figure here, it is the bar chart comparing protein adsorption and cell adhesion across different hydrogel types. Neutral hydrogels like PEG shows moderate protein adsorption, and ionic or cationic hydrogels have high protein adsorption and cell adhesion due to electrostatic interaction. Polyelectrolyte hydrogels perform better but are still sensitive to salts. But if we look at Zwitterionic hydrogels, they exhibit almost no protein adsorption and minimal cell adhesion, which visually confirms their superior antifouling performance. In short, we can say that Zwitterionic hydrogels outperform neutral, ionic, and polyelectrolyte hydrogels in terms of hydration, stability, and antifouling behavior, salt resistance, and biocompatibility. While earlier limitations existed in mechanical strength, modern reinforcement techniques allow Zwitterionic hydrogels to combine durability with their inherent surfaces property, making them the most advanced hydrogel class for biomedical, environment, and engineering applications. Challenges. Now I will move to one of the most important sections of this topic, which is challenges. Over the last 5 years, Zwitterionic hydrogels have rapidly evolved from laboratory scale antifouling materials to realistic biomedical and engineering platforms. However, despite this progress, several critical limitations still prevent their widespread industrial and clinical adoption. The first challenge that we faced in this regard is scalability and cost of monomer synthesis. One of the most significant challenges that we face is high cost and limited scalability of monomer synthesis. Even though these materials show outstanding antifouling and biocompatibility, producing them on industrial scale remains expensive. A detailed techno-economic analysis published in 2023 showed that the synthesis of MPC, which is one of the most widely studied zwitterionic monomer, remains cost prohibitive even under optimized conditions. At a production scale of 100 kilograms per batch, the cost of MPC exceeds 450 euros per kilogram. Approximately 68% of this cost came from the raw materials, largely due to the multi-step synthesis routes involving toxic intermediates, moisture-sensitive intermediates that require careful handling and purification. This cost is extremely high when compared to the conventional hydrogel monomers such as PEG-based materials, which typically cost between 25 to 50 euros only. This sharp cost difference is one of the primary barriers preventing large-scale commercialization of zwitterionic hydrogels. In response to this cost challenge, several innovative synthesis strategies have been emerged. In 2022, Bank and co-workers demonstrated a continuous flow synthesis of sulfobediene methacrylate that achieved 94% yield and 99.5% purity, while reducing reaction time from 48 hours to just 15 minutes. Importantly, this method completely eliminated the need of column chromatography, which is one of the most expensive and waste-intensive steps in chemical manufacturing. Another promising approach is enzymatic polymerization. A 2023 study published in Nature Communication showed that engineered lipase enzyme can directly polymerize zwitterionic monomers under mild conditions. This process avoids toxic metal catalysts and produces polymers with controlled molecular weight distributions, with dispersity values between 1.2 and 1.4, which is highly desirable for reproduced material performance. Microwave assisted synthesis has also shown great potential. Studies published in 2024 demonstrated that sulfobetaine methacrylate synthesis time could be reduced from 24 hours to just 30 minutes while maintaining yields above 90%. However, challenges related to the uniform heating and scale up still needs to be addressed before industrial implementation. Several practical solutions to deal with this challenge are also emerging. One particularly promising strategy is to use bio-derived zwitterionic monomers. In 2023, Shen and colleagues reported a one-pot synthesis using light-driven compounds that reduce production cost to below 150 euros per kilogram, while maintaining anti-fouling performance comparable to the commercial MPC. Another highly effective approach is copolymerization. Studies show that incorporating only 20 to 30 mole percent of zwitterionic monomers into the network made from low-cost monomers such as acrylamide can preserve antifouling behavior while reducing the total material cost by 60 to 70%. The figure here shows that this cost challenge and emerging solutions. The bar chart compares the production cost for different synthesis strategies. Traditional MPC synthesis appears at the highest cost around 450. When the flow synthesis is used for SBMA, the cost significantly drops to 280 euros. Enzymatic synthesis further reduces the cost to approximately 220 euros per kilogram. The most dramatic reduction are seen when the bio-derived monomers, which lowers the cost to around only 150 euros per kilogram. And with copolymer approach, where the effective cost can fall as low as 80 euros per kilogram. The downward arrow here in the figure visually represents this cost reduction trend. The lower part of this figure shows the innovative pathway for cost reduction. It begins with continuous flow synthesis, which streamlines reaction, reduces waste, and improves quality control. This is followed by the enzymatic polymerization, which use biocatalyst under mild conditions and avoid toxic reagents. Microwave assisted synthesis then accelerate reaction kinetics and reduce energy consumption. Finally, bio-derived feedstock provide renewable and sustainable raw materials that significantly lowers both economic and environmental cost. Mechanical performance integration. Second challenge is balancing the mechanical robustness with ultra low fouling behavior. A comprehensive study published in Science Advances in 2024 quantitatively demonstrated this trade off. Hydrogels with protein adsorption below 10 nanogram per square centimeters typically showed low fracture energies, often below 100 joules per square meter. Conversely, hydrogels with fracture energies exceeding 1000 joules per square meter often exhibited significantly higher fouling, with protein adsorption exceeding 15 nanograms per square centimeter. This clearly shows that improving mechanical strength often comes at the expense of anti-fouling performance. One of the major breakthrough in overcoming this challenge is the development of dynamic zwitterionic nanocomposites. In 2023, Liu and co-worker incorporated polydopamine modified MXCM nanosheets into the carboxybutane methacrylate hydrogel network. This material achieved a fracture toughness of 2.1 megajoules per cubic meter while maintaining fibrinogen adsorption below 5 nanograms per square centimeter. The key mechanism here is reversible catechol-zwitterionic coordination, which allows interfacial sliding and efficient energy dissipation without disrupting surface hydration. Another major advance came in 2024 with the development of topological interpenetrating network. A Nature Materials study reported a zwitterionic double network elastomer combining dynamic disulfide covalent bonds and ionically cross-linked zwitterionic chains. This system achieved a tensile strength of 4.2 megapascals, a fracture energy of 2800 joules per square meter, protein adsorption below 2 nanograms per square centimeter, and a self-healing efficiency of 92% within 2 hours at body temperature. Gradient network architectures have also proven effective. Using digital light processing, researchers created hydrogels with dense mechanical core and a soft, highly hydrated surface. This design maintains surface protein adsorption below 4 nanograms per square centimeter while achieving core toughness close to 100 joules per square meters. Looking forward, machine learning is increasingly used to guide formulation design. In 2024, Bayesian optimization was applied to identify optimal ratios of zwitterionic monomers, crosslinkers, and nanofillers. This approach achieved materials with fracture energies above 1500 joules per meter square and fouling below 10 nanograms per square centimeter in only 15 experimental iterations. Multiscale modeling that couples molecular dynamics with Continuum mechanics is now enabling prediction of mechanical and fouling behavior before synthesis begin. Long-term in vivo fate. Long-term biocompatibility and degradation behavior represents another critical challenge. A two-year implantation study published in 2023 examined carboxybutane methacrylate hydrogels in rat models. These hydrogels showed a gradual mass loss of 23% over 2 years, with degradation products consisting mainly of betaine and small oligomers that were safely cleared through the kidneys. However, not all zwitterionic systems behave identically. In 2022, studies showed that sulfobutane methacrylate degradation under oxidative conditions produced sulfonate-containing fragments that activated complement protein C3 in vitro, raising concerns about immunogenicity under chronic inflammatory conditions. To address this, a 2024 study introduced engineered carboxybutane methacrylate hydrogels with astrolinkages that enabled controlled degradation over 6 to 12 months. PET imaging in primate models confirmed the absence of inflammatory responses. Foreign body responses studied further demonstration that carboxybutane methacrylate coating reduces fibrous capsule thickness by 88% compared to the PEG after 12 months, and immune profiling revealed reduced neutrophil recruitment and a dominance of healing associated with M2 macrophages. A 2024 study on Zwitterionic hydrogel showed that these materials are generally well tolerated by the immune system. They reduce neutrophil recruitment by 67%, maintained regulatory T cell presence, and did not trigger detectable antipolymer antibodies. However, CD4 plus T cells responses were observed in 15% of the animal implanted with certain sulfobutane methacrylate formulations. To address these challenges, researchers are exploring immunomodulatory designs, such as incorporating CD47 mimic peptides to spread macrophage activation and matching the hydrogel degradation rates to tissue regeneration, which has shown promise in cartilage repair. Additionally, real-time monitoring of the implant environment is possible using hydrogels that include fluorescent sensors, which are sensitive to pH or reactive oxygen species, enabling in situ tracking of immune and tissue responses. We talk about the future directions. Looking towards the future directions, future Zwitterionic hydrogels are expected to evolve into smart, multi-responsive systems. For example, glucose-responsive insulin drug delivery systems combine phenylboronic acid with carboxybutane methacrylate networks, enabling insulin release in response to elevated glucose levels. This offers a promising route towards closed-loop diabetes therapy. Enzyme responsive drug delivery uses hydrogels that release drugs only when exposed to disease related enzymes like those in tumors, which helps target the drug locally and reduce the side effects. On the other hand, redox responsive systems use disulfide bonds that stay stable in bloodstream but break inside the cell when the environment is more reducing. We can say that where the concentration of glutathione is high, allowing the drug to be released inside the cell. Advanced manufacturing. Advanced manufacturing is enabling new possibilities for Zwitterionic hydrogels in regenerative medicine. 4D bioprinting with Zwitterionic bioinks allow the printed structures to change shape or properties over time in response to the body signals like temperature or ions, enabling self-fitting implants and maturing vascular structures. Spatial patterning techniques such as digital light processing can create scaffolds with regions that can resist or promote cell adhesion, useful for complex tissues like bone cartilage interfaces. New Zwitterionic chemistries. New Zwitterionic chemistries are also being developed. Peptide based zwitterines allow precise control over the structure and hydration while resisting degradation, improving biological interactions. Sulfamides and sulfonium zwitterines can adjust dipole strength and stability, potentially offering better antifouling properties or new responsive behaviors. Machine learning. Machine learning is emerging as a powerful tool for accelerating material discovery. By training the models on molecular descriptions and experimental data, researchers can predict antifouling performances, swelling behavior, and mechanical strength before synthesis. Ultimately, inverse design approaches may allow researchers to define target properties and automatically generate optimal monomer and network structures. If we look at the figure here, it represents a timeline linking the future directions with performance matrices. It shows how advances in smart systems, manufacturing, new chemistries, and machine learning are expected to progressively improve mechanical strength, anti-fouling performance, and biological integration over time. So, to conclude my assignment, I would like to say that Zwitterionic hydrogel represents a major advancement in functional soft materials. Their exceptional performance arises from simple yet powerful molecular principles. The formulation of a dense and thermodynamically stable hydration layer, while the challenges related to the cost and mechanical integration and long-term stability remains rapid progress in synthesis, reinforcement, and computational designs is steadily overcoming these limitations. As a result, Zwitterionic hydrogels are poised to play an increasingly important role at the interface of material chemistry, biology, and engineering. And these are all the references that I have used to make my assignment. Thank you so much for your time.